Yeah, we can see.
All right, good morning, guys. It is better than last time, the lighting. Yep. Okay. Ask your questions. I received two questions, 32, 33, 1.8. Any other questions from the homework? Just put them on the chat if you don't want to talk.
Can we do number 19 and 1.8?
1.8, number 19?
Yes, please.
Good. Okay, we still have 2 minutes, so you guys can look over your homework. All right. Good morning, everyone. We're gonna start. I'm gonna start looking at number 32. As usual, I would like your participation, whether in chat or just mute yourself and ask questions. So the first problem you guys asked me about the following, problem number 32. And we have the following transformation. It takes, now the book has a vector written in like x1, x2. You can write it either way. For us, R2 is the collection of all pair of numbers. You can write them this way, or you write them in vector notation, which is the one we really use because with this notation, we can multiply by matrix. And this notation is not useful for us. So that's really the idea. It takes x1, x2 to that. And the question is, show that T is not linear. It's not linear. And let us recall from last time, what does linearity mean? Linearity means T preserves vector addition. It means image of the sum is sum of the image. And T preserves scalar multiplication. It means if you take a vector, scale it, then find its image, it's the same as scaling the image itself. So that's T preserves scalar multiplication. To show that T is not linear, we have to convince me that either this property failed, usually it's easier to start here, or this one failed. One of them failed. And you can do that by giving me an example. It means giving me a vector U, a scalar, and show me that this property failed. So let's go back to this problem, and who can give me an example to show me that this property failed? Go ahead. Means I'm expecting from you a scalar and a vector such that this property here fails. Ideas?
The scalar should be negative.
The scalar should be negative. So, we will see why the scalar it should be negative. So I'm going to take C to be -1. And U, does it matter?
No.
I don't think so. Let's take 2 to be the vector 2, 3. And then in a minute, you will see what's causing this, why we need a negative scalar. Of course, whenever there is absolute value, negative, start giving me issues. And now let us make sure that the property actually is failing. So I'm going to compute T of Cu. Now, what is Cu? Cu, it means minus U. So Cu is, according to your choice, is minus U. So it means you're multiplying Q by a minus. It means that's T of -2, -3. But now, what does T do to a vector? It does the following. It's 4 times the first component minus 2 times the second component. So it's 4 times the first component. So it's -8. Minus 2 times the second component, which is 6. What's the second entry of the image? It's 3 times the absolute value of your second component. That's what it is. So now let's compute that. That's going to give me -2 in the top, and absolute value of -3 is 3. That's going to give me a 9. What if I compute minus T of U? So what is C of TU? So basically, can I take the minus out? It's minus T of U. But what's minus t of u? It means minus t of 2, 3. So it means minus what? What does t do to the vector 2, 3? The first entry is 4 times the first component, which is in 8, minus 6, twice the second component. What about the second entry of the image? It's 3 times 3. So this is going to give me minus 8 minus 6, that's it, 2, 9, which is going to give me minus 2, minus 9. And of course, t of cu, which is minus the u, is definitely different than c of tu. Linearity is failing. All right? Questions? Now, what's really causing the problem in here? What's causing this whole problem? Which piece is causing it? Ideas? The absolute value. That's what's causing the whole problem. The absolute value. This is really causing the problem. So let me show you on a separate sheet of paper what's really happening here if for the C. So let us say, so the problem is done as far as you guys are concerned. Linearity failed because the second property isn't satisfied. But watch what's happening in general. Suppose I compute T of C times a vector U, U1, U2. You can write U1, U2, you can write X1, X2, I don't actually care. It means that's T of CU1, CU2. That's the picture in general. Sorry, those don't belong. It means this is equal to, so let us see what this is equal to. It's 4 times the first component minus twice the second component. And here, what should go? It's 2 times the absolute value of CU2. Now the question is, here I can factor out my C for the first entry. Can I factor out the C in the second entry? What do you think?
No.
Why? Because
if it was negative, it wouldn't be the same.
Exactly. And that's why the linearity is breaking. So when I had, this is really what the problem is. When I had the absolute value of C times U2, we cannot take away the C. Because take, for example, as we did before, that takes C to be -1 and U2 to be 3, then the absolute value of -3 is definitely not minus the absolute value of 3. So it's really the absolute value which making the linearity totally break. All right, questions about this problem? Okay, very good. So I'm going to look at number 33 and then number 19. Number 33. So here my transformation does the following. It takes a vector x1, x2 to the following vector. So this is the entry of my new vector. It's 2x1 minus 3x2. So that's 2x1 minus 3x2. The second entry is x1 plus 4. And the last entry is 5x2. And show me that this transformation is not linear. And this is an easy one. I mean, a quick one. I want ideas.
You can just check for T of 0.
Okay, we're going to check T of 0. And last time we said that if the transformation is linear, it has to take the 0 vector to the 0 vector. And this is definitely, this plus 4 is just staring at us. So T of 0, in this sense, 0, it means the 0 vector. It means the vector that has for entry 0, 0. It's equal to 0, 4, 0. This is not the 0 vector. T immediately not linear. Okay. All right. So now we're going to move to problem number 17, which is actually the introduction to what we're going to be working on today. So it fits very well into our lecture. So number 17, number 19. So I'm working on number 19, section 1.8. Yeah, 1.8. Okay, so let's do that. And James is asking me number 17. Okay, I'll look at number 7. No, I'll look at 17 first because I want to use 19 as an introduction to our new topic. So I do 17 first. So let's read 17. 17 tells me the following. You have a T from R2 to R2. And what does T do? It's linear. It means it satisfies the two property of linearity. And T does the following. It maps U into 2, 1. How do we read this? It means the image of the vector 5, 2, that's what it means, is equal to 2, 1. That's what it means. It maps 5, 2 into 2, 1. And so this is my U. That's my U. And it maps the vector V. It means the image of V, which is 1, 3, it maps it into the vector minus 1, 3. And now the question is, use the fact that T is linear to find the images under T of 3U, 2V, and 3U plus 2V. I will only do the last one, and the picture will be clear for the others. So I want 3U plus 2V. Okay, so how are we going to use linearity? What does linearity tell me? Image of the sum is sum of the image. It means if I have a plus in here, so this is the same thing as T of 3U plus T of 2V. That's preserved addition. Also, my map preserves scalar multiplication. It means the 3, I can pull it out. So that's 3 times T of U. The same thing, this 2 should be pulled out. 2 times T of V. And what is T of U? What T does, it takes the vector U to 2, 1. So that's the image of that. 2, 1. Plus, it takes the vector V to minus 1, 3. So now we just add them. So I will have 6, 3 plus minus 2, 6. I'm going to add those vectors because that's the only thing they want me to do for now. Check. All right. So now we're going to move to the last problem, which is, as I said, going to be the beginning of today's lecture. My problem here is, okay, my problem here is the following. So now I'm going to look at number 19, which is I tackled at the end of the lecture last time, but now we're going to do it a bit more detailed. And I will use number 19 for that. So here we have E1, which is by now you should know what E1 is because we're going to use those. E1 are the unit vector. They are the I and J for U from 261. So E1 is the vector 1, 0. E2 is the vector 0, 1, the unit vector. And I have Y1, which is the vector 2, 5. And Y2 is the vector minus 1, 6. And also we have the following thing. T from R2 to R2 is linear, and it maps E1 into Y1. It means T of E1 is Y1, and T of E2 is Y2. Very good. So the question is, find the image of 5 minus 3. So we need to find T of 5 minus 3. Using all this info, we have to do it. Okay, let us remember. Let us recall. How can I write 5 minus 3 in terms of E1 and E2? Remember?
5E1 minus 3E2.
Because what's 5 minus 3? So it's 5 times 1, 0. That's one way. Minus 3 times 0, 1. So this is going to give me 5E1 minus 3E2. So I started by writing this vector as a combination of E1 and E2. Why? Because I know where E1 goes, I know where E2 goes. The linearity is going to help me to know where any linear combination of them is going to be sent. So now let us do T of minus 5, 3. So I'm going to use linearity now. So it's going to be equal T of 5E1 minus 3E2. Means it's what? Linearity tells me preserve vector addition. It means I can break here, so, and then I can take away the scalars. So it means that's 5 times T of E1 minus 3 times T of E2. All right? Now, I know what's T of E1, and I know what T of E2. So I'm gonna find everything. T of E1, according to them, is Y1, is 2, 5. T of E2 is Y2, which is minus 1, 6. And then I can compute the whole thing. It's gonna give me 10 plus 4, 14, 25, 25, you take away 18, 25, you take away 18, you get 7. Questions? Any question? All right, now we're gonna do the same one, but instead of 5 minus 3, x1, x2. And this is gonna start exactly basically this is my new material. So, but I'm gonna use the same problem because that's what it is. So my problem now, find T of x1, x2. I'm gonna do it exactly in the same way. So T is linear. I know where E1 and E2 goes. I wanna find what happened to any vector. So those two information will give me anything. All right, let's do this in the same way. So step number 1, I'm gonna write x1, x2 as combination of E1 and E2. So we should know that this is x1, E1 plus x2, E2. That's what it is. Now I'm gonna use linearity. Again, these are scalars. Those are the scalars. Those are the weight of the linear combination. And E1, E2 are my vectors. So it's gonna be x1, T of E1, plus x2, T of E2. Okay, so it's gonna be equal to what? x1 times T of E1, that's my y1. This is 2, 5. And T of E2, that's my y2, which is minus 1, 6. Now, at this stage, I want to write this as a matrix times a vector. So instead of computing, I'm going to write this as a matrix times a vector. What is the matrix? And what is the vector? So this is just the only thing I know about T, it's linear. I know what it does to E1 and E2, and I'm trying to find what it does to any vector. All right, what are the matrix? The first column is gonna be 2, 5.
Excuse me, Professor, could you write just a little bigger?
Yes, I will. Thank you
Thank
very
you.
much. I sure will. Minus 1, 6. All right, so once after that, I'll start right way bigger. All right, do you understand where this 2, 5 comes from and minus 1, 6 comes from?
Yeah.
Remember, this is the definition of a matrix times a vector. It's the linear combination of the columns of A, where the weight are x1 and x2. So if I multiply this by that, this is x1 times 2, 5, plus x2 times that. So let me write it a little bit bigger because this is going to be crucial. So basically, what I'm writing is this. This is 2, 5. And this is minus 1, 6. So T of x1, x2 is actually equal to this matrix times this vector. What's this matrix? The first column of the matrix is nothing more than T of E1. The second column of the matrix is nothing more than T of E2. And this vector is x1, x2. So let me sum up a little bit what's happening in this picture. We know that T is linear. And we know what T does to the E1 vector, T of E1. And we know what it does to T of E2. But this shows me that if you take T, apply it to any vector x1, x2, we know where it goes. It's the matrix A with this matrix times x1, x2, where this matrix has for column T of E1, T of E2. We're going to give this matrix a name, and we're going to call it the standard matrix of T. Okay, so now we're going to repeat this and state it within a theorem, that this whole idea. So let us go back. I'll go back to my notes now, to the lecture, because this is really part of the lecture. And here is the general setting. So I will read it carefully. So what is the general setting? Let T be any transformation from Rn to Rn, be a linear transformation. Then I know it's linear. We can show it geometrically linear. I told you it's linear. Then this transformation will be given by the rule T of x equal A times x. So the minute you know that your transformation is linear, then it's going to be given by a matrix A times x, where A is T of E1, what T does to E1, the first column. The second column, T of E2. The last column is T of E1. This matrix A is given a name, and it's called the standard matrix of T. And we denote it by T within bracket. So T with bracket means the standard matrix. It means the matrix whose columns are the image of the unit vector E1, E2, all the way to En. And I would like to note that T is a M by N matrix. So the number of columns is N, because I'm going to have all the unit vector of Rn, and the number of rows is M, because this is the image of E1, so it should be in Rn. Let us practice those ideas. Okay, so the first problem is going to be a fairly straightforward, just to understand the picture, and then we do more interesting one. So example number 1, suppose T is from R2 to R4, wherever it's linear. And I tell you where 1, 0 goes. So minus 1, 2, 3, 4. Those are irrelevant, basically, what the numbers are. And E2, that's my E2, is minus 1, 2, 0, 3. Find the standard matrix of T. So the standard matrix of T is nothing more than the matrix whose columns are T of E1 and T of E2. So what I put here, right there, this is nothing more than T of E1, minus 1, 2, 3, 4. And what I'm putting here, nothing more than 2 of E2. So that's what we mean by the standard. What's the benefit of the standard? The standard matrix tells me the following. It's going to allow me to find the image of any vector I want. So I tell you here, so this is my standard matrix in this particular problem. So that's it. Minus 1, 2, 3, 4. That's T of E1. Minus 1, 2, 0, 3. T of E1, T of E2. That's what it is. What's the benefit? The benefit is the following. Suppose I tell you for this T, find T of any vector, 2, 3. Anything you want. The standard matrix tells me that image of any vector is the standard matrix multiplied by 2, 3. That's what it tells me. Means if I want to know where 2, 3 goes, I take my standard matrix and I multiply it by this vector. That's what it is. We multiply it by this vector. And this makes sense according to what we did before, because this is 2, 3 has for entry 2, 3. So I'm telling you that 2, 3 could be written 2E1 plus 3E2. So T of it is 2 times T of E1 plus 3 times T of E2. So every linear transformation, if you know it's linear, and whether I tell you or geometrically we can convince ourselves it's linear, then T is given by a simple rule. It's matrix transformation. It's A times X. Please ask questions as we go on. All right, example number 2. Let T from R4 to R2. And it's given by T of X1, X2, X3, X4. We've done this before. X1 plus X2 and etc. My question is, find the standard matrix of T. What does this mean? It means I want you to find a matrix such that T of any vector is A times this vector. That's really what's find the standard matrix. Now in this particular problem, I'm going to do it in 2 ways. First, we're going to do it by inspection. Okay, can I do it by inspection in this problem? Can I find a matrix such that T of X is the matrix times X? We've done it before, X1 plus X2 plus X4. So 1, 1, 0, 1. That's going to be the first row. The second is minus 1, 2, 1, 1. That's what it is. Now, I'm going to apply, I'm going to find it in a different way as well. So the way we're going to find it now, so my transformation, take another sheet of paper. That's my transformation. T of X1, X2, X3, X4 is, according to me, X1 plus X2 plus X4 and minus X1 plus 2X2 plus X3 plus X4. Okay, so I'm going to do it a different way to apply the previous problem. It means T transformation T, the standard matrix, is T of E1, T of E2, T of E3, and T of E4. All right, let's compute T of E1. E1 is 1, 0. So what is T of E1? Sorry, E1 is, because I am in R4, is T of 1, 0, 0, 0. So what's T of 1, 0, 0, 0? 1, 0, 0. So it's 1. And here I have minus 1. So it means T of E1 is 1 minus 1. What's T of E2? Can you guys tell me what's T of E2?
1, 2.
1, 2. Do you agree with him? Anybody agree with him?
Yeah.
Yeah, because what's E2? What is E2?
0, 1, 0, 0.
It's 0, 1, 0, 0. So what is this? I'm sorry, sir. Okay, so T of 0, 1, 0, 0. So what is T of 0, 1, 0, 0? The first component, I'm going to have 1, And right here, I'm going to have 2. So that's 1, 2. T of E3, we can do the same thing. It's 0, 0, 1, 0. So this is going to give me a 0 in here. That's going to give me a 1. And if I find T of E4, I'm going to again get the same thing, 1 and 2. So regardless how you find this matrix, whether by inspection or you use the formula, we're going to get exactly the same thing. So there is one matrix that implements the transformation. All right, now more interesting problems. Okay, now I'm going to take the following. Let T from R2 to R2 be the linear transformation that reflects a vector across the line x1 equal x2. So now I'm taking the following type of transformation, more geometric. So the transformation does the following. That's the line x1 equal x2. And it does this. Takes a vector x and reflects it across the line x1 equal x2. So that's T of x for me. And the question is, this is a linear transformation. Geometrically, think about it, it's linear. And the question is, find the standard matrix of T. Basically, I'm asking you, find the matrix such that T of x is given T times x. It means, what's the matrix? If I know it, I know the image of every vector. All right, and this is where this idea that we're developing become interesting. To find the standard matrix, I need to find what T does to E1 and what T does to E2. If I know that, I know everything. All right, I'm going to do this properly, purely geometric. So what does T do to E1? So we're going to sketch it. So we're going to sketch the vector E1. And I'm going to ask myself, what does it do to E1? So I'm going to, again, do it here. This is E1. I'm going to reflect it across the line x1 equal x2. What does T do to it? It means, what is T of E1? Can anybody give me an answer?
Reflects it onto the x2 axis.
I'm going to reflect it. What does T of E1 equal to? Anybody?
E2.
What?
E2.
E2, absolutely, E2. It's actually the vector 0, 1. Now, I'm going to do the same for E2. What is T of E2? This is my vector E2. And I'm going to reflect it across x1 equal x2. I reflect E2, reflect, reflect. We're going to have E1. So T of E2 is going to be the vector 1, 0. So T of E1, 0, 1. T of E2 is 1, 0. What does this mean? That's exactly what I tried to explain in here. So what does this mean? So T of E1 is 0, 1. T of E2 is 1, 0. Means the standard matrix of T is 0, 1, 1, 0. What does it mean to you? It means the following. If I ask you, now that I have the standard matrix, so the standard matrix now is the following matrix, 0, 1, 1, 0. That's called the reflection matrix. What's the benefit? So now we know how to find it. And what's the benefit for it? The benefit is that I tell you find T of anything for 2, 5. Means if I take the vector 2, 5, so that's the line x1, x2. And if I take the vector 2, 5, so this is my vector right here. That's 2, 5. I take it and reflect it across the line x1 equal x2. So I'm going right there. The question is, what's the coordinate of this vector? That's the benefit of this transformation. So this tells me that if I know the standard matrix, T of 2, 5 is nothing more than you take your standard matrix and you multiply it by the vector 2, 5. If I do this, I just multiply them, I get 5, 2. It means I take the vector 2, 5, I reflect it, this new vector has for component 5, 2. So that's how we can find the standard matrix of the reflection. So we just have, so that's purely geometrical example. If I need the matrix for the reflection, okay, that's a linear because geometrically it's linear. And we take E1, we say, okay, what happened to E1? What happened to E2? Once we find what happened to E1 and E2, the standard matrix is the first column, be careful, the first column is important, that's T of E1. The second column, it's not this, what T does to E2. Once I know the standard matrix, I know what happened to any vector I want. It's just the standard matrix times the vector. And that's give me the image of any vector I want. Okay, questions please as I move on. Questions? Making sense?
Yeah.
Right on the chat. Okay, now.
Yep.
Sorry, I don't have those in order. I need them in order. Okay, that's the order. Right, my last example we're gonna work on is the rotation matrix. So what is the rotation matrix? So we're gonna take R theta from R2 to R2 with the following transformation. It's the transformation that rotates a vector x by an angle theta about the origin. So what is R theta? R theta is very natural question, very nothing really. It's very interesting transformation. What it does is the following. It takes a vector. Suppose I'm going to take theta to be, let us say, pi over 4. What does R theta do? I give it a vector, x. It's going to take this vector and rotate it. It's going to rotate it by pi over 4. When I rotate this vector, I'm going to end up with another one right there. And the question is, if I know what the vector is, let us say this is the vector 2, 1. And I rotate it by pi over 4. Just take it, rotate it by 45 degrees. You end up here. What are the coordinates of this new vector? Okay, that's really my goal. You take any vector, rotate it, you get a new vector. Okay, what are the coordinates of this new vector? That's the question that we're going to address right now. So what's the rotation function or the rotation transformation? The rotation transformation is basically the following transformation. You start with a vector, you rotate it by an angle theta, you end up somewhere. This new vector is called R theta of x. It means the vector obtained by rotating x by an angle theta. So that's really my problem. Now, so R theta is a transformation that take x, rotate x by an angle theta about the origin. Now R theta is linear, geometry, and we're gonna just see it geometrically. What does it mean? Linear. Watch carefully. Suppose I take the vector u. So I try to draw this as clear as I can. This is my vector u, and this is my vector v. And I'm gonna rotate u by an angle theta. So this is u rotated. And I'm gonna rotate v by an angle theta. Okay, so this is u, that's the rotation of u, and that's the rotation of v. So what does it mean, preserve vector addition? It means, is the rotation of the sum the same thing as the sum of the rotation? Means if I take this vector u plus v and rotate it, is it actually going to be the sum of the rotation of u plus the rotation of v? What do you think? Those are your u and v. Actually, you just rotate the whole picture. The whole parallelogram is going to be rotated. If you rotate u and v, and you rotate this whole parallelogram, it's going to be rotated right there. It means the u plus v, when you rotate u plus v, it's going to be exactly the sum of the rotation of the vector u plus the rotation of the vector v. That's really linearity, the image of the sum. So where does u plus v go? If you rotate it, it's going to go exactly to rotation of v plus the rotation of v. That's exactly where it's going to go. It means that it's going to preserve vector addition. Scalar multiplication follow very easily. If you take a vector, so scalar multiplication is going to be like that. You start with a vector. Suppose you have a vector u, and you rotate it. You're going to land right here. So if you stretch this vector, c times u, and you rotate it, where is it going to land? Is it going to land here? Yes or no?
No.
No. Is it going to land here? When you rotate cu, is definitely going to land right there. Right there. That's the rotation of cu. It's going to be exactly like if you take the vector, this vector, and stretch it by a factor of c. That's rotation linear geometry. And that's the easiest way to show it linear, is really to look at it geometrically. Now, if it's linear, now we can find the matrix that is going to help us to generate it. So let us look at the rotation matrix. Okay, so let us find the standard matrix of rotation. To find the standard matrix of the rotation, we need to find what does theta do to E1 and what theta do to E2. Again, we're going to do that geometrically. Okay, so we're going to geometrically decide what happened to E1 and what happened to E2 geometry. So I take it and I want your trigonometry here. So to find our theta of E1, this is my E1 right here. That's the unit vector. I'm going to take E1 and rotate it by an angle theta. I'm going to get here. And my question is, what are the coordinates of this vector? All right. I need your help. So this is E1. This is 1. It means 1, 0. I rotate it. I land here. What are the coordinates of this new vector?
The x1 coordinate would be E1 cosine of theta, and the x2 coordinate would be E1 sine of theta.
You're kind of correct, but I don't know where the E1 is coming from.
As well as just it would be cosine of theta and sine of theta.
Right. What's the coordinate of this vector? If you guys remember your geometry, this point here is cosine theta, sine theta. Okay, if we do it like in the basic stuff. Remember, I draw the picture one more time. This is the E1 I am rotating. If I am rotating E1, it means from here to here, it's 1. I rotate it, it means this is 1. Let me call this angle, that's my angle theta. So what are the coordinates of this point? That's really what I'm asking for. I can take you back to basic geometry. What's the cosine of theta? What's the cosine of theta? It's the x coordinate, which is right there, over 1. So the x coordinate, so cosine of theta, is the x coordinate over 1. So it means this x coordinate is the cosine. What's the y coordinate? Just look at the picture. The y coordinate is nothing more than the sine of theta. So if you take E1, you rotate it, you end up with cosine theta, sine theta. That's E1. Now what about E2? What about E2? Means if I take E2, that's E2, and I rotate it by an angle theta. I'm going to land here. And the question is, what are the coordinates of this new point? This is my angle theta, and I rotate it. What do I get?
Sine of theta, cosine of theta.
We're not going to get sine theta, cosine theta. But first of all, if you look at the picture, the x coordinate is actually negative. Simple picture.
Yeah.
All right, so if this is theta and this is theta, the x coordinate is going to be minus the sine of theta. And the y coordinate, this one, is going to be the cosine of theta. So that's a little bit of trigonometry applied. So our theta of E2 is minus the sine of theta, the cosine of theta. So now let me go back to my note where those are spelled out. So, and here the idea is, if we use basic trigonometry, our theta of E1 is the cosine and sine. Our theta of E2 is minus sine and cosine. So what's the standard matrix of the rotation? The first column is what it does to E1. The second is what it does to E2. So the standard matrix is cosine theta, sine theta, minus sine theta, cosine theta. It's usually a matrix that students basically memorize. That's simple as that. That means that if I have any vector x, I rotate this vector. Where does this vector go? It's the rotation matrix times the vector x. Immediately application. Okay. So problem number one is the following. Suppose I have t from R2 to R2, and no, that's not it. Sorry, that's the hard one. All right. Okay. For example number 4, suppose I have a vector 2 minus 1, any vector, I picked it, and I rotate this vector by pi over 3 about the origin. And my question is, find the image of W under this rotation. So I take a vector, this is my vector here, it's 2 minus 1. I take it and rotate it by pi over 3. I land here. My question to you is, what are the components of this new vector? It means what's the coordinate of this point? All right. It's easy actually to answer this question once we know the rotation matrix. The rotation matrix is, that's bracket means the matrix. Without the bracket means the function. So the rotation matrix is cosine pi over 3, sine pi over 3, minus sine pi over 3, cosine pi over 3. That's the rotation matrix. Now, if you guys remember your trigonometry, cosine pi over 3 is a half, square root of 3 over 2, and this is minus square root of 3 over 2 and a half. What does this help me to find? It means that if I rotate any vector, what's the image? It's the rotation matrix multiplied by this vector. You just multiply it by. So it means you take your rotation matrix, a half, square root of 3, minus square root of 3 of 2, a half. You multiply it by 2 minus 1, physically multiply them. So now we multiply. So I get a half times 2, it's a 1, plus the square root of 3 over 2. And here I'm getting square root of 3 minus a half. And I use my calculator to estimate. I get 1.87, 1.23. What does this mean to you? It means you take this vector, you rotate it by pi over 3, you're going to get a new vector. What are the entries of this new vector? 1.87 and 1.23. All right. So it's really a very, I mean, if you guys try to do this geometrically by yourself, take a vector, rotate it, what you're gonna get, it's gonna be tried. And it's not gonna be a fairly simple problem. If you know this rotation matrix, it's actually fairly simple. You take the rotation, you multiply it by the vector, and you know exactly where you're gonna land after that. Okay, questions as I go on? Anybody? Are you with me? Yes or no?
Yes.
I
Yes.
cannot. Yes, I want more than one person because I don't see your faces. Remember that. It's not easy not to see your faces. All right, the last example, it's a little bit harder, but we're gonna try to do as much as I can. Okay. So in this example, we're gonna do the following. I'm gonna tell you, let T from R2 to R2 be the following. It does two things. Takes the vector first and reflect it. And after it reflected, it rotated. Okay, so what it does. Okay, that's confusing, not so much. So what it does is the following. It takes a vector, let's see a vector right here. That's a vector. It reflected, so it takes it down here. It does two things. And after that, it rotated somewhere. The vector end up here. So that's the starting vector. That's reflected and then rotated. So reflect, then rotate. Okay, that's what it does. And the question is, if I know the original vector, can I find the end vector? Right. So the idea that this is a linear transformation, we can prove it mathematically, we can prove it algebraically. But for us is we're gonna find the standard matrix. It means we're gonna find the matrix that has the property that if I know the original vector, the last one is this matrix I'm gonna find times the starting vector. That's really what my goal is. Now the theorem tells me to be able to do that, you need to find what T does to E1 and what T does to E2. Always follow E1 and E2. And that's exactly what I'm gonna do. I'm gonna take E1 and E2 and I'm gonna follow them. So how I'm gonna follow E1 and E2? So I use a lot of geometry in this in those problems, and I'm gonna follow E1 and E2. So, all right, so let me do that. E1, I'm gonna write bigger. I'm gonna take E1. And so I'm gonna draw the picture and I'm gonna do the algebra at the same time. What my transformation do to the vector E1? First, it does what to it? First, it's gonna reflect it. So that's reflect. When it reflected, where does it go? If you reflect E1 with respect to the x1 axis, what happened to E1?
Nothing really.
Does it happen anything to it?
No.
It's gonna stay E1, which is 1, 0. After I do that, I'm gonna rotate. When I rotate it by pi over 6, I'm gonna land here. What are the coordinates of that vector? You either memorize or you say, you know, I know the rotation matrix. So after I rotate it, this is gonna go to here. The rotation matrix, which is we found a minute ago, which was a half square root of 3 over 2 minus square root of 3 over 2 and a half times 1, 0. So this is gonna go to the following, a half square root of 3 over 2. So my E1 is gonna go to a half square root of 3 over 2. And that's exactly what I did right here. I started with E1, I reflected, nothing happened to it. And then I rotated. Where does it go? To be able to know where it goes, I take the rotation matrix multiplied by 1, 0. I get 1/2 square root of 3 over 2. Now I'm going to do the same for E2, exactly the same. I'm going to take E2. I'm going to reflect it. But E2 is different. If I take E2, that's my E2. And I reflect it. Where does E2 goes? All of you. Is it easy to know? We take E2, we're gonna reflect it. E2 will go down here. That's the reflection. So if I start with E2, that's my E2, and I reflect it across the x2 axis, it's gonna go to the vector 0, -1. That's what my E2 is gonna go. It goes right here to 0, -1. After I do that, I'm gonna rotate it. I'm gonna rotate it right there. When I rotate it, we're gonna land here. Now, when I'm gonna land here, how can I find that's pi/6? How can I find this vector? You can either use trigonometry, or if you forget it, I say to find it, I take the rotation matrix and I multiply it by 0, -1. So I do that. This time that is 0. Minus minus plus, sine pi/6 is square root.
It's one half.
Oh, it's 1/2.
Yeah, I was gonna say everything I did was flipped, and I think I think you flipped it.
Then because, oh my God. Yes, because in my head, everything is pi/3. Okay, change everything to pi/3. Everything. Because that's in my head. That's what I am thinking. Pi/3. I will rewrite this and put it on blackboard with pi/3. I don't know why I put pi/3. Everything for me is pi/3. That's what I was thinking when I was doing the problem. All right, I rewrite with pi/3, but the idea is the same. I get square root of 3/2 and -1/2. So finally, what is my standard matrix? The first column is what T does to E1, which is 1/2 square root of 3/2. The second is what it does to E2, square root of 3/2 and -1/2. That's how we find the standard matrix. The last idea that I don't have time to do it today, but I would like you to read it carefully, and I will go over it quickly, is that we can do this problem in a very different way. We can find the standard matrix as a product of two matrices. So for your homework next time, on the top of your homework, I want you to read the last page very carefully, and I will go over it with you again, because we can find those really two ways, either follow E1 and E2, or as a product of two matrices. And that's the other idea I would like to emphasize next time. Okay, any other questions? Any questions before you guys go for your quiz? Questions? How did it go? Were you able to follow well? Yes or no?
Yeah.
Yeah,
Yep.
I heard one student.
Yeah.
Okay,
Yeah.
all right.
Yeah.
So now what I want you to do, you guys go to Blackboard. On the content area, there is a link called quizzes. Okay, are you, okay, I want all of you go to Blackboard. Okay, there is content area quizzes. Okay, you go there, there is quiz, I think it's quiz 7 in the content area. Are you guys finding it?
I see it.
What?
Said, yeah, I see it.
Okay,
Yeah.
everyone, you should be able to see it because I opened it. Yeah, it's open right now. All right, write yes if you guys saw it, or scream yes, I wanna know.
Yes.
Yes.
Yeah.
Okay, great.
I
Now,
can't seem to
with
find the
7.
actual document though.
All right, you click on the icon on it's written quiz 7.
Oh, all right. Okay.
Okay, it should open up for you.
Mhm.
You guys all have it?
Yeah.
I see it.
Yeah.
Yeah.
Yeah. Now the quiz is not a hard quiz. So you guys take a clean sheet, neat sheet of paper, not just anything, a neat sheet of paper. You write your quiz on it. You don't have to rewrite the questions, but you're very clear. Right, number 1, A, B, C, very neatly. Remember, it's a big class and I have to read all of you. It's not, then after that, if you can scan it, fine. If you can't, take a good picture of it and upload it into Blackboard. You know how to upload it.
Where are we sending it to exactly on Blackboard?
On the same page where you have that you open, then there is somewhere, I don't know what you guys see, that's the problem. But somewhere they say browse my computer.
If you click the quiz 7, not the download
Yeah.
link, there's a thing to attach files.
Yeah, okay, I see it now.
You see it? Yeah,
Yeah.
but I don't know your end, I know mine. Okay, all right. Once you're done, you have up to, I opened it till 11:05. Now, one more thing, that the time on Blackboard is West Lafayette time. So even if it says 12:05, it's actually 11:05. Don't ask me why, that's Blackboard, not me. So you guys take it. It should not take a lot of time. Scan or take a picture and upload it into Blackboard.
If we're able to print out the quiz to then just write on, like, have the quiz and write on that instead of doing.
You can do anything you want, but
Okay.
you have a time limit. You can do anything you want. Okay, so the quiz should not take a lot of time. I meant it so you guys practice this. You do anything you want, by 11:05 it's over. So you have to have it in by then. So I gave you a lot of time to do what you want. Okay?
Okay.
Get going. Good luck.